Hello, everyone. Welcome back. Today, I'm going to be talking about dependent and independent events. So, let's talk about what this means. So, independent events are two events that have no effect upon one another, then that means they're independent. So, for example, getting a tail on a coin flip and rolling a two on a die, they are independent events that have no impact on one another. So, I'm going to write that down. Getting tails, or it could be getting heads, doesn't actually matter, right? Getting heads, I'm just using this as an example. Getting tails on a coin flip, or B would be rolling some number on a die. We'll just say 2 on a die. These are an example of independent events, right? Because whether we get that tails or not, that's not going to impact what we roll in our die, right? Or vice versa. Let's say I rolled a 2 on my die. That doesn't mean we're more likely or less likely to get a tail when we do a coin flip, right? And so the formula for independent events is this, that if we have the probability of A and B happening is the same thing as the probability of A times the probability of B. Now, this is not true of all events. This formula is only true for independent events. When we have dependent events, then this is not the case. There's actually another aspect of this, element of this, we're going to have to include for dependent events, where the outcome of one depends is going to change the outcome of the other potentially, or change the probability of what's going to happen next, right? It's going to have some sort of impact on the other event and the likelihood that it has of happening. Okay, so let's do example one. Example one says a game consists of rolling a die, then drawing a card from a deck of cards, right? Now let's talk about that. Right off the bat, that sounds like two independent events, right? Because if we roll our die and then draw some card from a deck, then the die roll doesn't really have any impact on what card we draw, right? So therefore, independent events. Find the probability that an even number is rolled and a face card is drawn from the deck. So we know from this formula that all we must do is we must find the probability of A and the probability of B separately and multiply them together, and that will give us the probability of A and B. So probability A and B, or we could say A intersect B is another way to say this as well, or and, doesn't really matter, is equal to probability of A times probability of B. So in this situation, what are the probabilities? Let's let A be the even number on our die, so even number, and let's let B be, what was the second thing? Drawing a face card from the deck. So face card is going to be equal to probability of even number times probability of a face card. So let's think about that. Well, what's the probability of rolling an even number on a die? Well, let's see. The die has 6 numbers, 1, 2, 3, 4, 5, 6, and 3 of those numbers out of the 6 are, or half the numbers we could say, are even numbers. So therefore it's going to be 0.5, or 1 half. What's the probability of drawing a face card? Well, let's think about it. There's 52 cards overall in a deck, and face cards are which ones, right? Face cards are jacks, kings, and queens, right? And actually, some people consider aces face cards as well. In this case, we're not going to. We're just going to say jacks, kings, and queens are face cards. So that's 12 of the overall cards, right? Because we have, king of all 4 suits, queen of all 4 suits, and jack of all 4 suits. So all kings, all 4 kings, all 4 jacks, and all 4 queens make 12. So now if we multiply this together on our calculator, we're going to get, let's see, 0.115. So that's going to be our probability that we roll an even number and we draw a face card. So as you can see, not very likely. This number is closer to 0 than it is to 1. So therefore, it's not that likely that this is going to occur. We can write a quick conclusion statement here as well and say, therefore, the number of, or the probability of rolling an even number and drawing a face card is 0.115. And there we have it. All right, let's move on to example 2. Example 2 says, in Canada, the probability that someone is over 6 feet tall is 0.2. The probability that they have played hockey is 0.6, and the probability that they have blue eyes is 0.4. Assuming all events are independent, what is the probability that a Canadian is over 6 feet tall and plays hockey? Well, again, let's do that. Probability of over 6 feet tall and plays hockey. Let's say that over 6 feet tall is event A and playing hockey is event B. This would be equal to probability of event A times probability of event B, right? Using the same formula as earlier. Probability of event A of over 6 feet tall is zero point 0.2, as it said in the question. Probability of B, which is playing hockey, is 0.6. So we multiply those together, we get 0.12. So therefore, there's about a 12% chance that a Canadian, randomly selected Canadian from the population, is over 6 feet tall and plays hockey. So not that likely a chance. All right, now they're wondering, what is the probability that a Canadian is over 6 feet tall, plays hockey, and has blue eyes, right? So let's do that. The probability of over 6 feet and hockey and blue eyes is going to follow the same formula, except this time we have three events, A, B, and C, but the same logic holds true. All we must do is multiply the probabilities of each of the independent events together, and we will get the probability that all three of these things are true. So again, probability of over 6 feet is 0.2. Probability of hockey, of a randomly selected Canadian playing hockey, is 0.6. And the probability of a Canadian having blue eyes is 0.4, which actually I'm surprised it's that high. Blue eyes aren't all that common, but let's just say it is that 40% of people in Canada have blue eyes, which I don't think is true at all. But regardless, let's multiply those together when we get 0.048. So that means there's about a 4.8% chance, so a pretty low chance, that a randomly selected Canadian is going to fit all this criteria. And that makes sense, right? If we have criteria that is very, very specific, then it's less likely that it's all actually going to happen, because if any one of these things is not true, then the whole thing goes out the window, right? Then it's not right. It has to be someone who has all three traits, right? So and there's a lot more ways for someone to not have all those three traits. Someone could have two of the three, someone could have one of the three, or someone could not have any of the three. So there's a lot more ways to, not fit into this category than to fit into this category, because it's so specific. And that's generally true. The more specific we make our categories, the less likely we are to have somebody fit into that exact category, right? If I ask, well, how many people in this room like the color blue? A few people raise their hand, and then I say, okay, how many people like the color blue and also like hamburgers? Right? Probably less people raise their hand. Some people probably don't like hamburgers. Okay, what's the probability you like that? How many people in this room, like blue and like hamburgers and like the band? What's a band name? Can't think of a band name. Let's see. Or like the singer Taylor Swift, for example. Probably some people lower their hands, right? And so the more specific I make it, the less people are raising their hand and the less likely you are to choose somebody with all those characteristics, right? Because at some point, most people are going to lower their hand because they're going to say, oh, well, that last characteristic doesn't describe me, right? So there you go. Okay, so that's independent events. Now I'm going to be talking about dependent events. Yeah, I think we'll do that in this lecture as well. So basically, events are the opposite of independent events. Basically, when the probability of event B depends directly on the outcome of event A, then that's a dependent event. So I'm going to give an example of a dependent event. So let's say we want to know the probability of winning 3 games in a row, right? In this case, we must win the third game after winning the first 2 games, right? We need to win the first 2 games in order to win the third game, in order to have this outcome be the case, right? Let's say that I didn't win the first 2 games, well, then it's impossible to win those 3 games in a row, right? I need to win a third game after I've already won 2 previously in order for this to be true. And so the previous events do matter in terms of the outcome here. Let's talk about a conditional probability of B. The probability of B and then this line A is the probability that B occurs given that A has already occurred. So we have a formula here that says that the probability of A and B is equals to the probability of A times the probability of B given that A has already occurred. Now, why is that the case? Because we must assume that A has already occurred and give the probability of B based on that in order for both to happen. With the last formula, it didn't matter whether or not A had already occurred. It was just probability of B, regardless of if A occurred or not, because they were independent events, but now we have dependent events, right? Where probability of B only is what it is if probability, if event A actually did occur. And so we have to verify that event A did occur in this scenario in order to get the answer correct. Good. Now, with independent events, keep in mind that it doesn't matter because probability of B given that A did occur is the same as probability B because event A doesn't actually matter to us. So it doesn't really matter whether event A occurred or not. If I ask you, for example, what's the probability that I will roll a 3 on a dice or on a die, given that it is true that yesterday I went fishing? Well, you might say, well, those things have nothing to do with each other regardless of whether you went fishing or not. The answer is 1 in 6 that will roll a 3, obviously, right? Or what's the probability of, what's another example for independent events? Circling back to independent for a minute here. What's the probability that if I flip my coin, I will get a head, given that last time I flipped a head? Well, it doesn't matter whether I flipped a head or a tail last time, they're all independent events, so regardless, it's just 1/2. However, there are certain times when the previous event B, what happened with A does matter, right? For example, if I ask, what's the probability that you will bring your umbrella today, given that it's raining today? Well, you might say, oh, well, then I'd be more likely to bring my umbrella given that it is raining than I would be if it wasn't raining. So in that case, it would matter, right? It's not that my umbrella causes the rain to come. It's the opposite. It's that if I see rain outside, I'm more likely to remember to bring my umbrella. If I see it sunny outside, then why would I think to bring an umbrella today if it's not raining right now, for example? So things like that. There's certain outcomes where what's happened previously or matters, or what happens with a different event matters for this event, right? Or for example, let's say we're rolling 2 dice, and I ask, what's the probability that I will roll number 8 overall if we add up the numbers, given that my first die was 4, right? Well, there's the thing, if my first die was 4, well, then we know that we need to get another 4 in order to get 8 total, right? So therefore the answer would be 1 in 6, right? 1 in 6 chance of that 4, so 1 in 6 is our answer. Whereas if I ask, what's the probability of rolling, a sum of 8 when we roll 2 dice, given that the first die was 1, right? What's the probability for sum of 8 on both dice if event A was that we already rolled a 1? Well, then the answer is 0. That's impossible, right? If we already rolled a 1, even if we roll a 6 on the other die, that only gets the 7, so it's impossible to make an 8 with a 1 and another number from 1 through 6. And so therefore, we would say, oh, it's not possible. The probability of getting an 8 is 0 given that we already got a 1 on one of our dice. Good. So those are some examples to kind of illustrate how sometimes two events have nothing to do with one another, right? Whether or not I went fishing yesterday, the probability of rolling 3 on a die is still the exact same. But in other cases, the probability of something happening is going to depend on whether or not something else has happened, or, whether or not something else is going to occur, right? So I'm going to go through an example next. I think I've given a good enough explanation for kind of the difference there, and why the formulas are different, because I think it's important to understand why are these formulas different in order to help move forward with these events. Okay, so example 3 says, a market survey estimates that the population of a home having at least one Twitter user is 0.4. The probability of a home having 3 or more cell phone users, given that at least one of them is a Twitter user, is 0.5. What is the probability that a home has at least one Twitter user and 3 or more cell phone users? So in this case, the implication is that if somebody is, a Twitter user, if we have one person in a household who's a Twitter user, then that's going to make a difference, right? If we have 3 or more cell phone users in the house, then they're more likely to have at least one person use Twitter as well, right? Because Twitter is something you can use on your cell phone, right? So that's kind of the implication here. Whereas, let's say nobody has a cell phone, well, then perhaps we're less likely to have a Twitter user because, you might need, I guess you could use a Twitter on a computer. But yeah, there's the cell phone is one way to do it, and so that's kind of the implication here that they're making. So let's go ahead with that. Event A is at least one Twitter user. Okay, good. And event B is 3 or more cell phone users, like that. Very good. Okay, so let's figure it out. Well, what is the probability of event A occurring given that event B has occurred? Well, let's see. The question says the probability of a home having 3 or more cell phone users, so event B, given that at least one is a Twitter user. Oh, I've done this backwards. My apologies. The probability of event B happening, 3 or more cell phone users, given that A has already happened, there's at least one Twitter user, is 0.5. It tells us in the question. And what's the probability of A, event A, at least one Twitter user? It's 0.4. So therefore, the probability of A and B in this case is equal to probability of A times probability of B given A, which is equal to 0.4 times 0.5, which is 0.2. So therefore, there is a 20% chance, or 0.2 probability chance, that a home has at least one Twitter user and 3 or more cell phone users. Very good. All right, let's do example 4. It's one more example regarding dependent events. It says here, a high school basketball player goes to the line to shoot 2 free throws. So he goes to a line, he's shooting and seeing what he gets. Find the probability that the player made 2 free throws, given that it is known the player made at least 1 free throw. Assume the probability of making a free throw for a high school student is 50-50 or 0.5. So event A is making 2 free throws. let's say event B is that we've already made one free throw. Or that it is known that at least one free throw is made, right? So, therefore, we want to find out what is the probability that two free throws are made given, so probability of A, given that B is true, given that we already made one free throw. Well, here's the thing. We know that the probability of A and B is equal to the probability of B times the probability of A given B, right? So therefore, we can fill out everything except for probability A given B, right? It tells us that the probability of B making at least one free throw is 0.75, right? Now, how do we know that? Well, the probability of making one free throw is 0.75 or 3 and 4 for this reason, because we have an equal chance of missing or hitting, right? So either we miss both times, or we hit once, miss, or we miss once, then hit, or we hit twice, right? So 3 out of those 4 outcomes are going to result in us making at least one free throw, right? Because we could do win-win, we'll do win-win, win-loss, loss-win, or loss-loss, right? 3 out of these 4 things contain a win, right? Where we got at least one free throw. Now, what's the probability of A and B happening? Let's think about that. The probability that we made 2 free throws and one free throw already, right? Well, let's think about that. 2 free throws would only be this 1 in 4 chance, so 0.25 for that one, right? So therefore, probability of A given B is equal to 0.25 over 0.75, right? Which means probability of A given B is equal to 1/3, right? So therefore, the probability that we make 2 free throws, given that we made one free throw, is 1 in 3. And I should word this differently, that we made one free throw or more. It's not necessarily already, because I think that word kind of implies a specific timing or a specific order to things, and that's really not the case, right? The probability, and actually it makes a difference in the question, because the probability that we make one free throw but make a second free throw given we already made one, well, it doesn't actually change it then. But given that we know we're in one of these 3 categories, we're either in one of these 3 and we can't be in this one, well, it changes it. It makes it a 1 in 3 chance that we get the second one as well. Because we could have win loss or loss win, right? But we know that we're in one of these 3 options because it says given that we made at least one free throw already. We got at least one W, at least one win, right? Good. All right. Well, that is it for today. Next day, for our last lesson of the unit, we're going to be talking about mutually exclusive events. I won't get too into detail on that right now, but I will tell everyone about that for the next day. Good work, everyone, and we'll see you for the next day. Bye, everyone.